Design resolutions describe how much the effects of a fractional factorial design are confused with other effects. When you do a fractional factorial design, one or more of the effects are confounded. Although only a few of these designs are typically used, we will at least touch on all of them. In general, resolutions below 3 are useless, and resolutions above 5 are considered wasteful. Recognize that we want to use a fractional factorial design with the highest possible resolution for the amount of fractionation required. It is usually better to choose a design where main effects are confounded with higher order interactions. Let's begin by setting up some DOE nomenclature. For a full factorial design, the number of experiments can be calculated by raising the number of levels, L, to the power of the number of factors, K. For a fractional factorial design, the number of experiments can be calculated by raising the number of levels, L, to the power of the number of factors, K, minus the number of interactions that are confounded, P. We can also think of P as a reduction factor of the number of experiments. For example, if P equals 1, the fractional factor will be half the size of the full factorial. The generator tells us how to construct the interaction factors of the experiment. As you recall, if P equals 1, we half the number of experiments by creating one generator. If P equals 2, we reduce the number of experiments by a factor of 4 through the creation of 2 generators, and so on. A word is a collection of sequential letters. The defining relation is used to determine the confounding pattern of the design. It is a sequence of words that are equal to each other. The defining relation will have a number of words equal to 2 to the p power. A fractional factorial design allows for experiments to be conducted on a smaller set of meaningful interactions. These are determined by the defining relation. This allows us to save time and money, yet obtain useful results. We mention resolution 1 and resolution 2 for perspective only. Practically speaking, they are not very worthwhile or useful. A resolution 1 experiment consists of exactly one run and tests only one level of a factor. A resolution 2 experiment consists of main effects confounded with other main effects. A resolution 3 design is a fractional factorial design in which no main effects are confounded with each other, but the main effects and two-factor interaction effects are confounded. Resolution 3 designs are known as screening designs. Examples would be new products or troubleshooting production processes that are in trouble. Resolution 4 designs are best for characterizing and describing. They are very useful for robust systems. Recognize that main effects and two-factor interaction effects are not confounded. However, two-factor interaction effects can be confounded with each other. Resolution 5 designs are highly capable of finding small interactions. These designs deliver very little distortion. In situations where you are well funded, this would be a great option. There are Resolution 6 and Resolution 7 designs available. These are considered to be mostly fully factorial designs and considered wasteful. Many DOE texts offer a trade-off table of designs. Here is my spin on this instrument. On the left side, we have runs. Notice that these values are all powers of 2. The 2 represents the levels of each factor. On the bottom, we have the number of factors. This would be the exponent. If we raise 2 to each factor, we get the number of runs needed for a full factorial design. On the top, we have the reduction factor. Notice that each reduction factor traces diagonally through the table. On the far left, there is no value for the reduction factor. This means that there is no reduction, and if we trace that diagonal, we will get the full factorial designs for each factor. To use this table, start by deciding the number of the reduction factor. Now select the number of factors. Triangulate along the respective diagonal and up from the factor until your fingers meet. In the area, you will see the resolution for the design and a sequence of letters. Each sequence of letters represents a generator. Now look to the left of the number of runs in the fractional factorial design you have selected. Let's try one. Suppose we want a reduction factor of 2. This means that I will have 2 generators. Each generator will create an additional factor. We have 7 factors in our system. This would mean a full factorial with 128 runs. We do not have the resources for this. Instead of reducing the number of factors and potentially compromising the integrity of the design, we will instead pursue a fractional factorial design. Find the 2 in the top row and trace down to the right along the diagonal. Find 7 at the bottom and trace up. Our fingers should meet at the red oval. This tells me that the resolution of my design will be 4. This means that the shortest word in the defining relation will be of length 4. The 2 generators formed from the interaction of factors will be ABCD and ABDE. If we trace to the left, we see that this design will require 32 runs. This is far less than the 128 we originally planned for, and it's considered a 1/4 reduction. With this approach, all 7 factors can be represented in our design. There is a reason this is called a trade-off table. As we add more runs, we add more time and cost. Clearly, this will deliver the most informed decision. But in the real world, there are limits on what we can do. We must move toward more economical solutions, i.e., fractional factorial designs. Indeed, we will lose some resolution, but we will save time and money. Our ideal solution will be somewhere between these 2 extremes and be driven by the needs of the organization. Consider this test plan noted here. Suppose we have a system with 6 factors. To run a full factorial, we would need a run of 64 experiments. We have a limited budget and can only afford 8 experiments. One way to solve our issue would be to eliminate 3 of the factors, but this would be incomplete and likely not give us a detailed understanding of what is going on. Instead, we opt for a fractional factorial with p equals 3. 3 confounded interactions. Because we have p equals 3, this means there will be 3 generators, UV, UW, and VW. This is an eighth of a full factorial design. 8 experiments are derived from 3 columns for a full factorial. These are columns U, V, and W. Notice that the 8 experiments are the 8 combinations of pluses and minuses. To find the columns x, y, and z, we take the products of u, v, and w respectively, using element multiplication. For example, negative times positive is negative, and so forth. Now we need to figure out the aliases for this design. Since p equals 3, there will be 2 to the third, or 8 aliases. Let's start with our first generator. We have a rule we must introduce first. If we have 2 of the same columns side by side, this reduces to the identity. If we take the U column and multiply by the U column, you see we get the column of pluses. This is the identity. The identity is our first alias. Our next 3 aliases are found above to be UVX, UWY, and VWZ. Now we can multiply each of these words by the other to find more words. Remember to rearrange and combine. So the defining relation is I equals to UVX equals to UWY equals to VWZ equals to VWXY equals to XWZ equals to UVYZ equals to XYZ. The defining relation is noted here. Now we can use this figure to find out each factor and what it is confounded with. Start with U. Multiply U everywhere. Remember that any factor times I is just itself. If we ignore the third and fourth order interactions, since it is highly unlikely they will exist, this tells us that U is confounded with Vx and WY. In other words, we cannot tell U apart from the interactions of Vx and WY. Here are the aliases for the other factors. Looking at only the 2-factor interactions, we get the following. This helps us best define the behavior of our model. For example, the estimate for the U factor is actually the estimate of U plus Vx plus WY. The resolution is always equal to the length of the shortest word in the defining relation. This was 3. So we have a resolution 3 design. We are now ready to start our design. Remember that we want the highest resolution possible. This leans us closer to the full factorial design. However, we also want to include as many factors as we can. This pulls us more toward the fractional factorial design. As we add more factors, we reduce the resolution and the reverse. These two aims compete against each other. Make sure your objective is aligned with your design. Avoid eliminating factors in favor of a full factorial design. Without the benefit of any information, eliminating factors can be very risky. Ground your decisions in evidence from your experimental data as opposed to relying on your feelings regarding the importance of the factors.